Hello everyone, in this video we're going to be doing a question that involves the titration of a weak acid with a strong base. So let's just jump right into it. The question says we have a 50 milliliters of 0.5 molar HF solution that's going to be titrated with 0.25 molar NaOH, and the Ka of the HF is given. So remember, your HF is a weak acid, and in a given question, another way of figuring out if it's indeed in a weak acid or a strong acid. If they give you the Ka, that means it's got to be the weak acid. So before I do anything, I want to go ahead and write down the balanced equation between the acid and the base. So I'll go ahead and do HF plus NaOH, and then remember any acid-base reaction is going to make water and the salt. So in this case, once after making the water using OH and the H, we have left out the sodium and the fluoride there, so it's just going to be NaF. So it's extremely important to be able to write the balanced equation in these acid-base titrations. Um, Seems like it's already balanced. We have two hydrogens on both sides, one oxygen, one sodium, and one fluorine. Now, I do want to go ahead and write down what we are given. So we have 50 milliliters of this HF solution, which is technically going to be equal to 0.05 liters. And then I got 0.5 molar concentration of that solution. The NaOH is 0.25. I'm just going to go and write that down. And we're not really given the volume here yet because we're going to be titrating those as we move along. Um, in addition to writing the equation, also figure out how many moles of the acid you have present in the solution, because when you start titrating it, you got to figure out how many moles are being titrated by the given amount of base. So to find the moles of HF, I would do 0.05 liters of HF solution, and then use the molarity, which is going to be 0.5 molar, so zero point 0.5 moles of HF per liters. So that's going to be equal to 0.025 moles of HF. So that's going to be your initial moles of your HF acid. Now let's look at this first question. It says, what's going to be the pH when there is no NaOH added? So another way of saying all you really have is the HF. So since HF is your weak acid, I don't know how much it's going to be dissociating into ion. That's why we got to make a nice table here. So the HF, when it's by itself, it's going to be reacting with water, and it's going to set up an equilibrium with its conjugate base. So it's going to dissociate a little bit into ion, and then it's going to be making F minus. So our job is to figure out how much of this H3O plus we have in the solution. Because once we figure out the concentration of this H3O plus, we should be able to figure out what's going to be the pH of the solution. So we started out with 0.5 molar HF. So all those are going to be aqueous except the water. Since water is so much in amount, it's not going to affect the equilibrium. So we ignore the amount of water there. Initially, you don't have any of your products, and then if I lose X amount of HF, I should be making X amount of your products, both of your products on the other side, because they're all a 1-to-1 mole ratio. So that's going to be 0.5 minus X for the reactants, and I got X and X for the products there. Now, when I'm writing the Ka here, your Ka is going to be equal to, obviously, the concentration of H3O plus times the concentration of F minus, divide that by the concentration of HF. And then, obviously, that's going to be X squared, divide that by 0.5 minus X. And remember, your Ka is given to be 6.6 times 10 to the minus 4. Divided by 0.5 minus x here. So I don't want to be really dealing with a quadratic equation, so I want to see if I can ignore this x here And we can sure ignore this x because this 0.5 is going to be a lot bigger than this Ka value. And as a result, we can just assume that zero point 0.5 minus x is approximately going to be equal to 0.5. And in that case, let's say what your equation becomes, a 6.6 times 10 to the minus 4 is going to be equal to x squared divided by 0.5. So anytime you make an assumption, you usually have to state why you're making that assumption. So remember, this 0.5 is much bigger than your Ka value. Usually, if it's about 1,000 times bigger, then you're good enough to ignore that x and any x that's being added or subtracted. So then at the end of the day, your x squared is going to be equal to 0.5 times 6.6 times 10 to the minus 4. And then you got to take the square root of this on both sides to find the x. So let's see what that comes out to be. After doing calculations, I got 0.0182 molar concentration for H3O plus. So remember that X is going to be representing your H3O plus concentration. So since I know the H3O plus concentration now, we can go and calculate the pH by doing negative log of your H3O plus concentration. So negative log of that. So that's going to be 1. Well, I'm just going to go and write that down here. 0.0182, and that's going to be 1.74. So that's going to be your pH of this solution when there is no base added yet. So then let's move on now. So the next part of the question says, what's going to be the pH when you have 50 milliliters of NaOH added? So before we do anything, we got to figure out how many moles of the base acid you're going to be neutralizing when you adding this 50 milliliters of the base. So I got to figure out what's going to be the moles of NaOH here. So we are having 0.25 molar NaOH. So I'll go ahead and do 0.05 liters of NaOH, and then I'll do 0.25 moles of NaOH per liter, because that's your concentration there. So let's see what that comes out to be. So that's going to be 0.0125 moles of NaOH. Okay, so if I go back and use that equation that we have written out earlier, just going to bring that down here. I'm going to go ahead and make a so-called an ICF table here. You don't necessarily have to make an ICF table, but sometimes it's just the life is easier when you go ahead and make an ICF table in terms of moles and figure out how much you have neutralized. So initial moles of HF that we have calculated was 0.025 here. So I'll go ahead and write that down here. So initially you have 0.025. The NaOH that you're adding here is going to be 0.0125. And don't worry about water, and then you don't have any NaF assume in the beginning. And it's okay to assume that because you're not going to have too much of dissociation in the beginning anyways. So NaOH is going to be your strong base, and it's going to be your limiting reactant. So I would lose all of the NaOH, and in doing so, I would lose that much of your HF, or another way of saying 0.0125 moles of NaOH will be neutralizing 0.0125 moles of HF, and in the process, they're going to be making 0.0125 moles of NaF. So at the end of the day, I would have 0.0125 left here, no NaOH, and then the NaF is going to be 0.0125 here. Another way of saying we have reached at a point where you have neutralized half of the acid using this base. So when you have neutralized half of the acid, and another way of saying when the concentration or the moles of HF or your acid is going to be equal to the moles or concentration of your conjugate base, you are going to be at half equivalence point. So it's extremely important to be able to identify that you are going to be at half equivalence point. And remember, you're at half equivalence point your pH is going to be equal to the pKa. So all we really got to do is just figure out what the pKa going to be. So remember, the pKa is going to be negative log of the Ka, and then negative log of Ka is going to be 6.6 times 10 to the minus 4. Okay, so let's see what that's going to be. 3.18. So that's going to be the pH at the end of the day once you have neutralized half of your acid there. This is going to be the half equivalence point. Okay, moving along, what happens when you add 100 milliliters of NaOH? So again, figure out how many moles you have for the NaOH here. So I'm going to be having, I'm going to write that down here, 0.1 liters of NaOH, and then we are obviously starting out with 0.25 molar NaOH, so moles of NaOH per liter. So that's going to be 0.025 moles of NaOH. And then you can go ahead and make the ice table if you want, but then remember, you also want to be able to figure out how many moles you have neutralized without looking at or without doing the ICF table. And you can clearly see that you have 0.025 moles of HF in the beginning, and then now you're adding 0.025 moles of NaOH. That means you will be neutralizing all of your acid here, and that's when you're going to be at equivalence point. And I'm going to go ahead and write that out here now. So make an ICF table again. So yeah, HF is going to be 0.025 moles, and then NaOH that's being added is going to be 0.025 moles again. And we're going to be neutralizing all of this acid and base now because we've got 1 to 1 mole or an equal amount of acid and base there. So you don't have any of the acid in the at the end, and then you should be making that many moles of NaF there. So at the end of the day, you're going to have 0.025 moles of your NaF, which is literally the F minus, because that's what we're really going to be focusing on. So that means we are going to be at equivalence point. Now, since we are titrating a weak acid with a strong base, the pH at equivalence point should be a little bit over 7, and that's what we need to figure out. And that's usually the confusing part for a lot of students, that they can't figure out what's going to be the pH. If you were doing in a strong acid, strong base, then you don't really have to do any calculations. The pH would have been 7. But here, the pH is going to be greater than 7, and that pH greater than 7 is going to be obviously due to your conjugate base, which is going to be the F minus. And that's what we need to focus on now. So our job is to figure out first what's going to be the concentration of F minus there. So your F minus is going to be 0.025 moles, and that's going to be divided by the total volume. So remember, you have 100 milliliters of NaOH added, but then you started out with 50 milliliters of the original solution. So you're always going to be assuming in these titrations that your volumes are additive. So your total volume in this particular case, I'll go ahead and write that down here. Total volume is going to be 100 plus 50. So it's going to be 150 milliliters. I'm just going to double check. That's 50, yeah. So that's going to be 0.150 liters to be your volume there. So let's just go and do the math here. 0.025 divided by 0.150. That's going to be 0.167 molar. So now we got to go back and rewrite this equation in the form of F minus as your starting material, because you don't have any HF, but this F minus is going to be acting as your base because it's a base of a weak acid, a conjugate base of weak acid. So it's going to react with the water, and it's going to make some HF and the OH minus back in there. So it's going to be making HF and the OH minus. So since it's acting as a base, it must be producing the OH at the end of the day. So that's what we got there. So now we can go ahead and make an ice table now. So in this case, we're going to be making an ice table because it's going to be in the form of the concentration, not in the form of moles. So I'm starting out with 0.167 moles here. Don't worry about water. And then HF, you don't have any of those because initially you have neutralized all of it. If I lose X amount here, and I should be making X amount on the product side, so your F minus equilibrium concentration would be 0.167 minus X, and your HF is going to be X as long as, and also the OH minus. So if we can somehow figure out what's going to be the concentration of OH minus, which is represented by X here, we should be able to figure out the POH, not the pH directly, but then eventually we should be able to figure out what's going to be the pH there as well. So we're going to have to write this equation in the form of Kb, and we don't really know what the Kb is going to be for F minus. So that's another extra step that a lot of times students get confused. So remember, your Ka times Kb for a particular acid and conjugate base is going to be 10 to the minus 14, their product. So I already know the Ka, so I can go ahead and calculate the Kb by doing 10 to the minus 14 divided by the Ka, which was 6.6 times 10 to the minus 4. I'll just double check that back here. Yeah, 6.6 times 10 to the minus 4. And let's see what that comes out to be now. All right, after doing this math, I'm getting 1.52 times 10 to the minus 11. So that's going to be your Kb. So let's go back here and go and write that equilibrium base expression here. So Kb is going to be x squared divided by 0.167 minus x. And you can easily assume that 0.167 minus x is approximately going to be equal to 0.167, because look at it, this Kb is very, very small. So let's go ahead and put these values in there. So 1.52 times 10 to the minus 11, and that's going to be equal to x squared divided by 0.167. And let's figure out the x now. So that's going to be 0.167 rather, times 1.52 times 10 to the minus 11, and take the square root on both sides. So let's figure out what that x is going to be. So that comes out to be 1.59 times 10 to the minus 6. So this obviously is going to be your OH minus concentration. So I can go ahead and calculate the POH here, which is going to be negative log of that concentration, which is 1.59 times 10 to the minus 6. So let's see what that comes out to be. That's going to be 5.80. And then the pH is going to be 14 minus 5.80. It's going to be 8.20 as your pH at equivalence point. So remember what we predicted earlier, that at equivalence point your pH should be over 7, and we said that because we were titrating a weak acid with a strong base, and that does come out to be over 7. It comes out to be 8.20. Okay, so then this last one, it says what's going to be the pH after adding 110 milliliters of NaOH. Now, once you have passed the equivalence point, it's easier to kind of deal with those questions after that. All you really got to do is figure out how much extra base you have. So remember, you needed 100 milliliters to reach equivalence point. Then you worry about what's going to be your extra NaOH in there. So the extra NaOH would be just 10 milliliters in there after reaching the equivalence point. So figure out how many extra moles of NaOH you have. So I'll go ahead and write that down here. And that's exactly the thing you're gonna be doing if you're doing in a weak base strong acid titration. After reaching or after passing the equivalence point, you're only gonna be focusing on what's gonna be the excess of your strong acid or strong base. So extra moles would be, I'll do 0.010 liters, because that's how many extra volume of NaOH you have. And then you got 0.25 moles of NaOH per liter. So that's going to be giving you 0.0025 moles of NaOH. Okay, so then at the end of the day, what we're gonna doing here, we gotta figure out what's gonna be your concentration here. So to figure out the concentration of NaOH, I know the moles now, which is 0.0025 moles of NaOH, but then we also gotta figure out what's the total volume that has stacked up now. And remember, we started out with 50 milliliters originally, and that would have been 0.05, and now we added another 110 milliliters, so it's going to be 0.110. So your total volume would have been 160 milliliters total. So it's going to be 0.0025 divided by 0.160. So that's going to give you the concentration of 0.0156 molar. And also remember, this is a strong base or strong electrolyte, which is going to dissociate completely into ions. So that means your OH minus concentration is also going to be 0.0156 molar. And then we know the OH minus concentration, so that means we can go ahead and calculate the POH by doing negative log of this 0.0156 here. So let's see what that's going to be. That's going to be 1.81, and from here on we can calculate the pH by doing 14 minus 1.81. That's going to be 12.19. So that's going to be your final answer. So remember, after adding even a 10 milliliters of extra base, after reaching the equivalence, your pH changes dramatically onto the basic side, and since it's a strong base, it's going to be closer to the 14 in this particular case. So this is how you're going to be doing your acid-base titration, especially when you have a weak acid. Obviously, the important part to kind of point out here is the half equivalence point, and then how you deal with the situation once you reach the equivalence point, how you flip the equation and all that. And then obviously, once you pass over the equivalence point, how you're going to be doing your how you're going to be calculating your pH just based on the extra base, or in case of you doing in a strong acid weak base titration, then how much extra acid you have added in there. If you have any questions on any of those, feel free to leave any comments in the section.